Here's some homework help for section 2.3. These problems are taken from pages 107 and 108, and as you can see, this is number 6 on 107. So our goal here is to look at a graph and describe the end behavior. So let's just take a look. So end behavior means as we have larger and larger values for x, or our domain continually increases, going to positive infinity, what is that doing? What is the reaction then to the graph when that happens? So as you can probably tell, as our values for x approach positive infinity, okay, I'll just indicate it with that arrow, the value of y is also going in positive infinity direction for the y-axis, which is straight up. So putting this together in a statement, we'll say as x approaches, with an arrow, positive infinity. That's what I've done here. I'm showing as x gets bigger and bigger. Then the function, noted as f of x, does the same thing. It also approaches positive infinity. Okay? What we always want to do, that's end behavior, means what happens on the right end and on the left end of this graph. So going to the left, as x approaches negative infinity, which would be this way, then the graph, the function, also goes to negative infinity. And so because going down on the y-axis is the negative infinity direction for the y-axis. So as x approaches, I'm just going to put as again, as x approaches negative infinity, the function does that as well. Okay, and that's all there is to it. This would be your answer for number 6 on page 107. The next problem is a little word problem where you're having to figure out what we call extrema, and we need to understand what we mean by estimating zeros of a function. We talked about that in class. So extrema indicate points that we would call relative maxima and relative minima. And another way of thinking of these, you'll hear more and more about when you get into pre-calculus and calculus. These are points where the graph changes direction. Can you tell going from left to right, this graph is going up and up and up and up and up, and then all of a sudden it hits a point, and at that point it changes from going up to going down. See that? And then there's another point at which it bottoms out and changes direction again from going down to going up. And so in calculus we call these points of inflection. You may also hear them referred to as turning points. The graph actually turned directions at those two different places. Well, for us, I just want you to see that this red dot is a relative maximum. Okay, our graph reached a high point and then came down. It's like a peak. And then it reached a low point and started coming back up. It's like the bottom of a valley. So we have a peak and a valley. And these 2 points at the highest and lowest points of these two are called maxima and minima. Okay, so while we're on the subject of maxima and minima, let's go ahead and find out where these are. And here's 0. This is x's negative 1, and then negative 2 at this place, negative 3, and so forth. So it looks like, now this is a little tricky, and if you said you have a relative maximum at exactly x equals negative 1, I wouldn't necessarily count it wrong, but this is a little tricky. I probably wouldn't do this to you on the test. That's why I'm walking you through this. But it's good to be prepared for future math classes where this type of thing may show up. Do you see where our inflection point or our turning point or relative maximum isn't exactly on -1, but it is near -1. So that's why they're telling you to estimate the coordinates. Now, in our examples in class, we didn't have to estimate. We could tell exactly where they hit a grid mark. But in this case, you're actually doing the estimate just like we did with the zeros in our example. So if you were to say x equals -1, I wouldn't say that's terrible and it's wrong. I wouldn't mark it wrong, but I'm going to have you do this on this particular problem. The relative maximum is near x equals -1. Okay, that probably makes sense. It's just to the right of -1, maybe -0.75 or -0.8. I'm not really sure, but we just estimate to the nearest integer. Okay, and in a similar way, let's identify an estimate of the relative minimum. Okay, I identified the relative minimum here with this blue dot, and it's pretty close to +1, so I'm going to say it's near x equals 1. Okay, so we're good on the relative max and relative minimum, these two turning points. And now let's estimate the zeros. Well, there's actually only one. A zero is where the graph crosses the x-axis. It's actually an x-intercept. And the zero of this function is near x equals -2. Real close to -2 on the x, but not quite. So that would be the complete answer to this number 7 problem. And throwing some terms at you that I hope you'll start getting used to. In addition to relative max and min, these are known as inflection points or turning points. Okay, well, let's take a look at this word problem. This is on page 108, next page over. And this girl's parents have set up a college savings account. This graph represents the balance in the account over time. So let's see, can we answer letter A? What is the initial balance at the beginning? Well, it looks like it's $2,000, so that's not too bad. We'll say $2,000. Okay. Letter B is to describe the end behavior as x approaches positive infinity. Okay, so we've been doing this in previous problems. As x gets bigger and bigger and bigger and keeps on going toward positive infinity, then the function, the graph, is going the same direction, and it's going positive infinity along the y-axis, which is up. Okay, so as x approaches positive infinity, we'll say f of x, or the graph, also approaches positive infinity. Okay, so hopefully that makes sense. It's going to continue to go upward as the numbers for x get bigger. Okay, that takes care of letter B. Letter C, is there a turning point in this graph? Well, remember what we said about turning points? Those are like max and min points, points of inflection. And for this, it's just a straight line. There are no points which cause this graph to turn and go in a different direction. Or no points that to go in a different direction. I.e. a turning point, basically the definition. So what trends do this graph suggest? Well, a trend is what do we expect to continue to happen if this current condition continues? Well, as the years go on, as years increase, as we get further into the future, in other words, we would expect this amount to be saved to increase as well. I'll just say the account balance. And that's not too hard to understand. It's just a graph of a straight line has a positive slope, and it's going to continue on. Now, obviously, it shouldn't continue on indefinitely because she's eventually going to go to college and she won't need the savings account anymore. It will be spent, but that's more or less what letter E was asking about, which I did not require you to do. I just wanted you to do parts A, B, C, and D. All right, so I got a couple more, and I just, these aren't from your book. These are from that 2-3 practice sheet that you had to do in addition to the book problems. So I just thought I'd help you out with these. They're kind of interesting and maybe a little different. But anyway, we have the Consumer Price Index. Maybe you've heard of that before. This is given from September 2000 to July 2001. This graph represents that time period. So you got to think of it in terms of this is September, then this would be October, November, December, January 01, February, March, April, May, June, July, August, just abbreviating there. So since we're starting at September, then this would be the September mark and so forth. You probably get that. So describe the turning points, okay? We had a little discussion about turning points. Well, this graph has a little bit of a hump to it right here. You notice how these dots gradually get up to a certain point and then come back down. Okay, so that would be one of those turning points where we're going in a certain direction and then go in a different direction. And that point of inflection, or that turning point, looks like it's on November. Okay, then we keep going upward here. We have another point of inflection here at December. Okay, so you saw how we reached a peak, then we came down, and then we go right back up again. So there's another turning point. All right, and we're following this same, once we've turned and went a different direction, we're going up, we're going up, we're going up, we're going up until we get to here, and then we change direction and go back downward. Okay. So the question is, describe the turning points. Well, in what months do we have turning points that occur? Well, we already identified November, December, and way up here looks like June. Okay, and if you just put that, that would be okay, but this is one of those cases where we actually could have two relative minimums in this data, relative maximums, I'm sorry, where we have this little ridge, we reached a high point and then came back down. That would be a relative max. Up here, doing the same thing, reaching a high point and then coming back down, would technically be considered another relative max. And then this bottoming out point, you know, we reached a high point, came back down, it's a low point, and then started to come back up. Then that would be a relative minimum. So our November could be a relative maximum. June up here, also a relative maximum. And then the December, where it bottoms out, relative minimum. Now, you might be wondering, well, what about this point? Well, if we had another point to go on that, you know, maybe they don't tell us, they don't give us a point for this last line here on the graph, but what if it, for example, were here? Well, then we would have another relative minimum here because we're going to change direction again. We're going to go down, and then we're going to go up from that point. But if you can just identify more or less the months where you notice we change direction in the graph, to me that's the most important part of this. But if you can tell me, well, watching this video, you should be able to tell me that we actually have 2 relative maximums and then 1 relative minimum. Okay, this is my last one, same sheet. We have this jobless rate modeled by these ordered pairs. So you might think about, just, it doesn't have to be anything fancy, but start with this one. Let's just say that's 1, 3.3. 2, 4.9 would have to be a little higher. 3, 5.3, a little higher than that. 4, 6.4, a little higher than that. Well, then we go to 5, and we're going to drop back down to 4.5. Okay, well that was our 4.9. So we can kind of line it up to here. Okay, so that's 1, 2, 3, 4, and then for 5 we dropped considerably. Okay, the next will be 6, 5.6, and that matches up with our third, where this was 3, 5.3, so it's pretty close. 6, 5.6, and then we take another big dive, 7, 2.5. Okay, that's going to be below our first mark at 3.3. So maybe just a little plot, scatter plot graph, and just so you can kind of get an idea how many turning points would this graph have, and see if we can describe them. Can you tell if they're going to be relative maximums or relative minimums? Well, hopefully you can tell that we have a turning point here because we were going up and then all of a sudden we go down. Same thing happens here. We were going down, but then we hit this point and go up. And then same thing happens here. We were going up and then we hit this point and go down. And I need to get that other, what about this one? This 8, 2.7, which is just above the very last one. This was 7, 2.5, and so we'll call that 8, 2.7. So this, you may not have to do this. You might be able to tell just by looking at the ordered pairs how we're changing direction with this graph, how it's creating some peaks and valleys. All right, so this is our another turning point or point of inflection. We hit here after going down, we hit here and then bounce right back up. Okay, so there are 4 total turning points. Okay, 4 turning points. I circled them in red. And describe them. Well, 2 of these, the peaks, would be relative maximums. So we have 2 relative maximums here and here, and then these 2 points that bottom out would be considered relative minimums for this data. So even though they're not exactly the same, when you have a set of data like this, it's not uncommon to have 2 or more relative maximums or relative minimums. The graphs that I gave you from the book, you just had one of each, or there are times when you have like the W-shaped function like this, and I think we looked at this where we had 1 relative max and 2 relative minimums that were basically the same on the same level. So it is possible in this case, when our data follows this up and down pattern, we can have more than 1 relative max or min. So it's kind of interesting. I just wanted you to get a taste of these real-life word problems, and I hope this will help you. And if you have any questions, let me know.